Welcome back to the RBFS Fundamentals Training Series. In Part 1 of our BGP module, we explored the BGP state machine, path attributes, and the configuration and monitoring of external BGP sessions in great detail. In this second part, we'll expand your toolkit with additional options to help you optimize your BGP setup. All configuration examples and demos in this video are based on RBFS version 25.2.1. Before we dive deeper into the Border Gateway Protocol and its implementation in RBFS, here's a quick disclaimer. This video is free to use for non-commercial purposes and is designed to support your self-study journey with RBFS. Please note that it does not cover every configuration option available, and implementations may evolve in future versions. Now, let's take a quick look at what we'll be covering. First, we'll explore the differences between internal and external BGP and highlight some key implications. Next, we'll look at settings related to autonomous system numbers. Although route policies are covered in a dedicated video in this series, we'll walk through a few common BGP use cases here to help deepen your understanding. Then, we'll introduce BGP Communities, a concept closely tied to route policies that offers additional flexibility for optimizing your setup. Finally, we'll wrap up with a look at BGP Security Features, including the Generalized TTL Security Mechanism, BGP Flowspec, and Resource Public Key Infrastructure. In the first part, we learned that BGP is primarily designed to run between routers in different autonomous systems. This is called external BGP. However, in large networks, it's also necessary to run BGP between routers within the same AS to maintain consistency, also known as internal BGP. When configuring BGP, the commands are the same for both internal and external sessions. Whether a session is internal or external is determined by the remote AS configuration in the peer group. If the remote AS matches the local AS, it's an internal BGP session, otherwise, it's external. From an operational standpoint, though, there are key differences between iBGP and eBGP. The most important is that BGP path attributes are not modified when routes are advertised to internal peers. This has a major impact. As we've learned, the AS path attribute is used for loop prevention in BGP. If the AS path isn't updated, which makes sense for route updates within an AS, then there's no built-in mechanism for loop detection. As a result, a BGP speaker is not allowed to advertise prefixes learned from one internal neighbor to another. This is known as the BGP split horizon rule, and it requires that all internal BGP peers be fully meshed. Since BGP uses TCP as its transport protocol, iBGP sessions between internal routers are typically built using loopback addresses. The connectivity between loopback addresses is achieved by an IGP routing protocol such as OSPF or ISAS. In contrast to external BGP, where the TTL value is set to 1, the TTL value for internal BGP messages is set to 255 as the peers are not directly connected. However, the approach of building a full mesh of iBGP sessions doesn't scale well as the network grows. Another important attribute is the next hop, which also remains unchanged in iBGP updates. Because eBGP peers are usually directly connected and iBGP peers are not, this can lead to a situation where an iBGP peer cannot resolve the next hop of a route learned from another AS. On the flip side, some BGP attributes are exclusive to iBGP, such as local preference. Let's take a closer look at next hop processing. Imagine router R1 receives a route update from an external BGP peer, say R2. By default, in eBGP sessions, the next hop is automatically set to the peer's IP address. Since eBGP messages are sent with TTL set to 1 and no additional routing protocol is typically involved, the peer is usually directly connected. Now, when R1 advertises this route to its internal BGP peers, neither the AS path nor the next hop is modified. This means the next hop remains set to R2's interface IP address. To install this route into the routing table, a router must be able to resolve the next hop. This can be achieved either by redistributing the link between R1 and R2 into the IGP, or by rewriting the next hop using the command set instance default protocol BGP peer group name address family IPv4 unicast next hop self true. The same command exists for the IPv6 address family as well. As we've seen, the BGP split horizon rule prevents routes learned from one internal peer from being advertised to another, requiring a full mesh of BGP sessions. As the number of routers in an AS increases, the number of BGP sessions grows quadratically. To address this, RFC 4456 introduces the concept of route reflectors. A route reflector has two types of internal BGP neighbors, clients and non-clients. It breaks the split horizon rule by advertising IBGP learned routes to all of its clients and by advertising routes learned from its clients to all other IBGP peers. To prevent routing loops, two new BGP attributes were introduced, the cluster list and the originator ID. Each route reflector has a cluster ID, a 4-byte value usually written in IPv4 format and, by default, set to the router's ID. When reflecting a route, which means forwarding an IBGP learned prefix to a client, the route reflector adds its cluster ID to the cluster list. The first route reflector also sets the originator ID to the router ID of the internal peer from which it received the route. Before reflecting a route, the route reflector checks the cluster list to see if its own cluster ID is already present. If it is, the route is not reflected. It also ensures that it does not advertise the prefix to the peer identified by the originator ID. In large-scale networks, route reflector hierarchies can be built by making a route reflector the client of another route reflector. While it's common to modify BGP path attributes using policy, it is highly recommended to avoid this on route reflectors, especially setting the BGP next hop to self, which would cause the route reflector to attract traffic. A BGP peer becomes a route reflector by configuring one or more of its internal BGP neighbors as route reflector clients. In RBFS, this is done per peer group and per address family. The cluster ID can optionally be set to any 4-byte value. By default, a BGP router advertises only the best path as determined by its route selection process for a given prefix to its neighbors. This behavior can lead to suboptimal routing and even traffic blackholing during convergence events, especially when route reflectors are used. Consider a simple example. Routers R11 and R12 learn the same prefix from a neighboring autonomous system and advertise it to a route reflector. The route reflector selects the best path, say, via R11, and advertises only that path to its client R13. If R11 fails, traffic destined for the prefix may be blackholed until the route reflector detects that R11 is unreachable, withdraws the original route, reruns the best path selection, and advertises the new best path, via R12, to R13. This process introduces delay and potential packet loss. The BGP add path feature, defined in RFC 7911, allows a BGP speaker to advertise and receive multiple paths for the same prefix. To use this feature, both sender and receiver must support it and negotiate the capability during BGP session establishment. A 4-byte path identifier is added to the NLRI to distinguish between multiple paths. Returning to our example, with add path enabled, the route reflector can advertise both R11 and R12 paths to R13. If R11 fails, the IGP will typically detect the failure faster than BGP and remove the route to R11. As a result, R13 will mark the path via R11 as invalid and can immediately fall back to the alternative path via R12 which is already present in the BGP table and resolvable via the IGP. This eliminates the delay in path re-advertisement and reduces traffic blackholing. An additional benefit of BGP add path is that when multiple equally good exit points are available, a router receiving all paths can choose the one with the lowest IGP metric to the closest exit point, improving routing efficiency. The main disadvantages of using BGP add path are increased memory and CPU utilization due to a larger BGP tables. In this section, we'll look at some configuration options for AS numbers that differ from the default settings. These can be useful in certain setups. With BGP, you typically configure your local autonomous system number globally, and the AS number of each BGP peer within its respective peer group. But in some cases, it's helpful to use multiple AS numbers on a BGP speaker. This is common when migrating networks from one AS to another, merging multiple autonomous systems into one, handling acquisitions, or even rebranding. It's especially useful when legacy routers are involved, where old AS numbers shouldn't be touched. RBFS lets you configure a secondary AS number at the peer group level. This allows the router to appear as part of a secondary autonomous system to external peers. However, this must be done carefully, as misconfigurations can lead to routing loops. To advertise routes to the Internet using BGP, you need a unique autonomous system number assigned by an Internet registry. RFC 6996 defines ranges of AS numbers that are considered private. These numbers shouldn't be advertised to the public Internet. Private AS numbers are commonly used in lab environments, within organizations to manage traffic between units, sites, or data centers, and even for private connections between two organizations. This is also useful when a service provider's customers need to interconnect using BGP, for instance, to achieve multi-homing and redundancy, but don't have public AS numbers. In these cases, private AS numbers must be removed from the AS path before advertising prefixes to the public Internet. BGP relies on the AS path for loop detection. By default, a router will reject any BGP updates containing its own AS number in the AS path, preventing loops. But in some situations, a network might be split into multiple parts, with those parts connected by a third party. This is common in BGP MPLS L3 VPNs, where BGP is used for PECE routing. In these cases, BGP's loop detection could block valid updates if it sees its own AS number in the path, even if there's no loop. In the diagram on the right, AS 64501 is split across two sites. When a router in AS 64501 receives an update from either AS 64502 or AS 64503, it will reject the update by default, because AS 64501 is already included in the AS path. However, since there's no backdoor connection and we know it's safe, we can accept the update whereas number 64501 appears once without causing any BGP loops. RBFS offers a feature called Allow ASN that lets BGP accept its own AS number in the AS path for a certain number of times. While this can be helpful in split networks, it should be used carefully to avoid routing loops. It's time to put these configuration options into practice. We're using a virtual lab environment running RBFS version 25.2.1. The network topology consists of 5 routers, R1 to R5, each in a different autonomous system. The AS numbers are taken from the range reserved for documentation purposes, according to RFC 5398. Routers R2 to R5 are pre-configured, and will focus on configuring router R1. The BGP sessions to R2 and R3 are already up and running, so now we'll configure the BGP session to R5. We'll use the set instance protocol BGP peer group AS65005 command to create a new peer group, set the remote AS number to 65005, and activate the IPv4 unicast address family. Then, we add a new BGP peer using the set instance protocol BGP peer command. R5's IPv4 address is 172.16.0.22, directly connected to interface hostIF 0/0/11. We also assign the newly created peer group to this peer. After committing the configuration, we notice that the new BGP peer stays idle. Using the ping command, we can confirm that it's reachable. To inspect the BGP messages exchanged between R1 and R5, we use the capture interface hostIF 0/0/11 command. From the output, we can see that R5 sends an open message with its own AS number set to 65005. It also sends a notification message with the error subcode bad peer AS number, indicating it expects a different AS number than the one R1 is sending. This is a scenario where we need a secondary AS number to support our 5. To resolve this, we define another AS number, 65001, at the peer group level. After committing the changes, we verify that the BGP peering with our 5 is now established, and our 1 is using AS number 65001 instead of 64501 to connect to our 5. However, if we check the output of the show BGP ribout command, we see that both AS 65001 and the global AS 64501 appear in the updates sent to our 1. Since our 1 doesn't recognize AS 64501, we remove it from the AS path using the set instance default protocol BGP peer group AS 65005 replace as true command. After activating this configuration, we confirm that the global AS number has been removed from the AS path. Next, let's look at the BGP advertisements our 1 sends to our 2 and our 3. No surprise here, our 1 advertises prefixes learned from our 5, including both our 5's AS number and the secondary AS number in the AS path. Since both AS numbers are from the private AS range, they need to be removed before advertising to our 2 and our 3. While we could use a route policy to modify the AS path, RBFS provides the set instance default protocol BGP peer group name address family IPv4 unicast remove private AS true command, which simply removes all private AS numbers in the AS path. After running the show BGP ribout command again, we can confirm that the private AS numbers have been removed. Finally, from the show BGP ribbon command, we can see that our 1 is receiving 2 prefixes from our 5. We know there's a remote site in AS 65001 connected to our 5, but the updates are blocked to prevent an AS path loop. To fix this, we allow our 1 to accept updates from our 5 that contain its own AS number once in the AS path, using the command set instance default protocol BGP peer IPv4 172.16.0.22 172.16.0.21 allow AS in 1. After committing this change, we run the show BGP ribbon command again, and we see that there are now 3 prefixes, with 172.16.10.0/24 originating from AS 65001. Let's take a moment to summarize the commands we've covered in this demo. In addition to the local as command used in the set instance default protocol BGP level, RBFS also allows defining a local AS number at the peer group level. This feature mimics another AS number toward peers. The remove private AS command enables the removal of private ASN numbers from the AS path before advertising prefixes to neighbors. This eliminates the need for route policies. Finally, the Allow ASN feature permits a BGP peer to accept prefixes containing its own AS number in the AS path, which is particularly useful in BGP MPLS L3 VPN setups. BGP is a routing protocol that does more than just exchange reachability information and find the best path between source and destination. It's also driven by business logic, so implementing routing policies goes hand in hand with BGP. In this section, we'll show you some common policy configurations. There's a dedicated video in this series that covers how to configure routing policies in RBFS, but for now, we'll quickly summarize the policy framework. If you want more details, be sure to check out the policy video. A policy is made up of several sections called ordinals, each uniquely identified by an ordinal number and executed in that specific order. Each ordinal contains 2 parts, a match block and an action block. The match block holds multiple rules that define which objects are considered. If the match block is triggered, the corresponding action block runs, which may also contain multiple rules defining what happens to the matched object. Since a match block can have several rules, multiple actions can be applied at once. If there's no match, the process continues to the next ordinal. To make configuration easier, you can use policy lists, which define a set of objects, like prefixes, within the match block. Policy lists improve scalability and reduce errors. In BGP, policies are mostly used to evaluate route updates after they've been received from peers or before they're sent out to them. These policies are applied as import or export policies based on each peer group and address family. Since some filter rules apply to multiple peers and others are peer-specific, RBFS supports policy chaining, where multiple policies can be linked together and executed in sequence. This modular approach allows you to reuse common parts of your policies. Policies can also control the redistribution of routes from other routing sources, like static or direct routes, into BGP. Before we dive into some examples, let's quickly summarize the most common ways policies are used in BGP. Policies help control the advertisement and acceptance of both IPv4 and IPv6 prefixes. For instance, they can reject specific IP addresses, such as private IPv4 addresses, according to RFC 1918, IPv4 link local addresses, IPv6 link local addresses, or IPv4 unique local addresses. In the previous section, we discussed private AS numbers. For security, a BGP speaker should reject any BGP updates with AS paths that include private AS numbers, especially on public peerings. If the autonomous system you're working with is a service provider network, it should only accept prefixes from its customers that are assigned to them and prevent them from announcing external prefixes. On the other hand, if you're managing a multi-homed enterprise network, you might want to avoid turning it into a transit network. Beyond security, routing policies can influence the route selection process, often based on business considerations, like directing traffic to and from autonomous systems that offer lower costs or better performance, for instance, lower latency. One of the most common ways to control how traffic leaves your local AS is by modifying the local preference. Local preference is a BGP attribute used in internal BGP, typically set on the edge router and distributed within your network. Remember, local preference is the only BGP attribute where a higher value is preferred. You can't directly control which path traffic takes when entering your network, since the neighboring AS controls its own exit points through local preference. But you can still influence the decision by modifying BGP attributes before sending routing updates. The AS path length and the multi-exit discriminator are two commonly used attributes to achieve this. Let's start with a simple example. As mentioned earlier, the length of the AS path is one of the top criteria in the BGP route selection process. If two paths are available and you want to prefer one over the other for incoming traffic, artificially increasing the AS path length of the less preferred route is a common technique. In the diagram on the right, AS64501 advertises the same prefix with a normal AS path to AS64502, while it adds its own AS number twice in the update sent to AS64503. AS64504 receives this prefix via two distinct paths, one with an AS path length of 2, and the other with a length of 3. In the absence of additional policies, traffic from AS64504 would be sent via AS64502 to reach AS64501, due to the shorter AS path. While it is technically possible to add any AS number, the common best practice is to prepend your own AS number to extend the AS path. It is also crucial to add the AS number at the beginning of the AS path, not at the end, since adding it at the end could cause issues if the origin AS is validated by BGP filters. Let's quickly demonstrate this on router R1. The command show BGP ribout shows that AS number 64501 is added once to the AS path before sending updates to R3. Now, we'll configure a new policy named export_ISP3 using the set policy statement command. Since we want to apply the AS path prepend to all prefixes, we skip the match rules and go straight to creating an action rule. The action is of type asPath, since we're modifying the AS path attribute. The operation is prepend. This adds our own AS number at the beginning of the AS path. We then add a second action rule with the operation goToNextOrdinal, so the policy continues evaluating with the next ordinal. This is important when modifying BGP attributes, as you often don't want to terminate policy evaluation right away if there are additional actions or matches to be made. Finally, we add ordinal 99 to accept all prefixes, as the default is to reject anything that isn't explicitly accepted. This allows us to add more ordinals to the policy later if needed. Next, we need to apply this policy to router R3 as an export policy, using the set instance default protocol BGP peer group ISP3 address family IPv4 unicast command. Once the configuration is committed, we can verify that AS number 64501 appears twice in the AS path. Alright, to wrap things up, I've summarized the configuration steps that we just went through for your reference. In addition to manipulating the AS path attribute, there are various use cases where filtering based on entries in the AS path is necessary when receiving BGP updates. The policy framework supports standard match types such as exact, exists, and regex to handle different scenarios. With exact, the AS path must match the given value exactly. With exists, it's sufficient for the AS path to contain the specified AS number. Although regular expressions are powerful tools, when matching entries in the AS path, it is often more convenient to treat an AS number as an atomic value. In RBFS, there are specific options optimized for this purpose: origin, transit, and neighbor. The neighbor refers to the directly connected peer AS, meaning the first AS number in the AS path. The origin refers to the AS where the prefix was originally injected into BGP, which is the last AS number in the path. The transit type matches all other AS numbers in the AS path that are neither origin nor neighbor. RBFS also provides a way to directly match the length of the AS path without needing to define a complex regular expression. Filtering on AS path length helps network operators prioritize shorter, more direct routes and avoid unstable or suspicious paths that may indicate misconfigurations or security risks. It's a simple yet effective way to enhance routing performance and safeguard the network. If the same rules apply to multiple AS numbers, you can simplify the configuration using policy lists of type AS path, which define a set of AS numbers. Additionally, AS path policy lists support the definition of AS number ranges, which is useful when matching a continuous block of AS numbers, such as private AS ranges. We'll demonstrate these filters using 3 simple examples. We examine the BGP prefixes received from router R2. The prefix 172.16.50.0/24 originates from AS 64505. Suppose we don't trust this AS and want to block it. We create a new policy statement called ASN_filter and add ordinal 1 with a match rule of type AS path. Since we want to match a single AS number, the value type is set to discrete. To match the first AS number in the path, we use the match type origin, and then set the appropriate value. The corresponding action rule uses return deny to reject these prefixes. This policy is applied to peer group ISP2 as an import policy. Because the default action of a policy is to reject all unmatched prefixes, we need a rule to accept the remaining ones. We do this by creating a second policy statement named import_ISP2, with a single ordinal 99 and an action rule to accept everything. This policy is also applied to ISP2 as an import policy, forming a policy chain. We repeat the same steps for peer group ISP3, reusing the ASN_filter policy but adding a new import_ISP3 policy. After committing the configuration changes, we verify that the prefix 172.16.50.0/24 is now blocked. Now, we focus on prefixes 172.16.51.0/24 and 172.16.52.0/24. Both contain a private AS number in the AS path. Filtering individual AS numbers isn't scalable, so we create a policy list named private_ASN, also of type AS path. Instead of listing numbers, we define a range. We set the subtype to range, then add ordinals to define the start and end values. Ordinal 1 includes 2-byte private AS numbers, and ordinal 2 includes 4-byte private AS numbers. We then update our existing ASN_filter policy by adding a second ordinal, again of type AS path. This time, the value type is list and the match type is transit, since we want to match any private AS number used as a transit AS. The value is set to the name of our policy list. The action rule again uses return deny to reject matched prefixes. After committing the changes, we confirm that the filtering works as expected. Finally, we turn to prefix 172.16.53.0/24. Its AS path is quite long, so we want to block it. We add ordinal 3 to our ASN_filter policy. The match rule is again of type AS path, but this time the value type is length, allowing us to match based on the number of entries in the AS path rather than specific values. We set the match type to greater or exact and define the value as 5, meaning we'll match all AS paths of length 5 or more. For demonstration purposes, the action is set to return deny. Once the configuration is activated, we confirm that the prefix is successfully rejected. Let's briefly summarize the configuration steps from this demo. To simplify match rules, we can use policy lists of the AS path type to define which AS numbers should be matched. Ranges can also be specified. Here, value 2 sets the end of the range. Beyond the familiar match types exact, exist, and regex, AS path matching also supports neighbor, transit, and origin. Values can be provided either as individual AS numbers or as policy lists. Additionally, policies support matching based on AS path length, using an integer combined with a numerical relation. Now that we've thoroughly explored an AS path policy example, let's shift our focus to the multi-exit discriminator, commonly known as MED. MED is an optional, non-transitive BGP attribute used to influence how inbound traffic enters your autonomous system. It works by affecting a neighbor's route selection process, where lower MED values are preferred over higher ones. This attribute is only used on external BGP sessions between the same neighboring autonomous system. And it's important to note, MED values received from one AS should not be passed along to others. In the example shown, AS64501 has two links to AS64502. It prefers traffic to arrive via the upper link. To guide this behavior, it advertises the same prefix with two different MED values, 50 for the preferred path, and 150 for the backup. The configuration below shows how this is done. The action rule is set to type MED, and we use the overwrite operation to assign a new value. If a MED value already exists for the prefix, you can also use operations like add, subtract, multiply, or divide to adjust it. Earlier in this section, we mentioned that the primary BGP attribute used to control outbound traffic from your AS is local preference. Unlike MED, local preference is only used on internal BGP sessions. Let's look at another scenario. AS64501 receives a prefix from AS64504 through two transit autonomous systems, AS64502 and AS64503. Suppose AS64503 offers lower transit costs. In that case, we want to prioritize it and treat AS64502 as a backup. To do this, we set the local preference to 150 for AS64503 because with local preference, higher values win. In the configuration snippet below, we define the action rule type as local preference and overwrite the value with 150. Since local preference only applies to internal BGP sessions, overwrite is the only relevant operation if the policy is applied as an import policy to an external peer. Now that we've covered BGP routing policies in some detail, let's take a closer look at how operators control routing behavior. This brings us to BGP Communities, a powerful tagging mechanism that enables more granular policy enforcement across networks. BGP communities are like sticky notes attached to routes. While they don't influence the BGP route selection process directly, they signal how routers should treat specific routes. These tags are passed along with the route and help simplify policy management by marking routes for future processing, either within the same AS or by external BGP peers. When autonomous systems agree on what these communities mean, they can even coordinate routing behavior between networks. BGP communities are added and removed from routes using routing policies. They can be applied in both import and export policies and can also be assigned during route redistribution into BGP. Communities are optional transitive attributes, meaning they are propagated across BGP speakers even if some routers don't understand their meaning. The standard BGP community, as defined in RFC 1997, is a 32-bit value. It's usually written in the format AS number : where the first part is a 16-bit AS number, and the second part is a 16-bit value assigned by the operator. Because standard communities only support 2-byte AS numbers, BGP large communities were introduced in RFC 8092. These are 96-bit values divided into three 32-bit blocks which are separated by colons. The first holds the 4-byte AS number, and the second and third are operator-defined values. Additionally, RFC 4360 defines extended BGP communities, which are 64-bit values. These include a typed field that determines the community's meaning. A common example is the route target extended community, used to define VPN topologies in BGP MPLS VPNs. Now, let's talk about some predefined communities with special meanings. The no-export community tells routers not to advertise the route outside the local AS, while the no-advertise community takes it further, advising not to advertise the route at all. BGP communities have a wide range of uses. They can help coordinate routing behavior between networks. For example, two autonomous systems might agree on specific communities to signal how traffic should be handled, including the no-export or no-advertise community we've just covered. They're also powerful tools for traffic engineering. Operators can steer traffic along preferred paths, or route it through specific MPLS tunnels, just by tagging the right communities. During a denial-of-service attack, a route can be marked with a black hole community to tell upstream routers or upstream ISPs to drop malicious traffic in order to mitigate denial-of-service attacks. In large networks, BGP communities are often used to encode geography like regions, cities, or data centers. This makes it easier to apply location-specific policies, for instance to reduce latency or to manage costs. These policies can also be used to meet regulatory compliance, such as ensuring that certain traffic stays within defined jurisdictions. BGP communities also make life easier for network operators. Instead of writing long, complex routing rules, you can just tag a route with a community and let the policy engine handle the rest. Finally, communities help with monitoring and troubleshooting. They make it easier to track how routes move through the network, and how they behave along the way. Without BGP communities, routing policies can get messy. Communities let you tag routes with meaning, making your policies cleaner, faster, and much easier to manage. Let's jump back to router R1 and check whether we are receiving any routes that already have communities attached. As we can see, there are two prefixes with standard communities. One prefix has 3 communities, and another has 1. All of these communities are assigned to AS 64504, which is not directly connected to our local AS. Therefore, we want to remove these communities. We update our existing policy statement import_ISP2 by adding a new ordinal. In this new ordinal, we define a match rule of type community. We set the value type to discrete and the match type to exact. This rule should match the community 64504:123. In the corresponding action rule, we use the operation delete attribute match, which deletes communities matched in the match block. As a second action, we specify to proceed to the next ordinal. After activating the configuration, we check the received prefixes again, but we notice that nothing has changed. The reason is that we specified match type exact, but the first prefix has 3 communities, while we only defined a single value. This results in no exact match. To fix this, we change the match type to exists, which means it's sufficient if at least one community matches. After committing the updated configuration and reviewing the output again, we observe that one community has been removed from the prefix. As we stated earlier, our ultimate goal is to remove all communities attached by AS64504. To achieve this, we modify the policy match rule once more. This time, we set the type to regex and configure the value to match all communities from AS64504. After activating the configuration again, we confirm that no prefixes remain with any communities attached. Let's summarize how communities are handled in BGP route policies within RBFS. There are 3 types of communities that can be matched: standard 32-bit communities, large communities, and extended communities. When you're defining communities in a policy, you can either specify them directly using what's called value type discrete, or you can reference a predefined policy list using value type list, depending on the type of community you're working with. To match these communities, there are a few options. You can use an exact match, which requires the entire community list to match exactly. You can use exists, which checks whether at least one of the specified values is present. Or, for more flexible pattern matching, you can use regex, which matches based on a regular expression. Now, if you want to modify an existing community or add a new one to a prefix, you'll need to create an action rule. This rule can be of type community, large community, or extended community, depending on what you're targeting. There are 3 main operations you can perform in the action: adding, replacing, or deleting. Append adds the new community at the end of the list, while prepend adds it at the beginning. But since communities are treated as unordered lists in BGP, it doesn't really matter whether they're added at the beginning or the end. The key thing to remember is that both append and prepend preserve existing communities, while overwrite replaces them entirely. In each case, you'll need to specify the community value you want to apply. You also have the option to delete communities. You can either remove the entire community attribute, or only delete those values that were matched in the match block. To make operations easier and avoid relying too heavily on IP prefix lists, RBFS offers a convenient feature: you can assign communities directly to an interface IP address or to a static route. This is especially useful because interface addresses and static routes tend to vary across routers, while communities often remain consistent. That means your policies can be written in a more generic and reusable way, making management simpler and more scalable. Let's wrap up this section on BGP communities with a practical example. Remote triggered blackholing is a technique used to stop unwanted traffic, especially during denial-of-service attacks or distributed denial-of-service attacks. Take a look at the diagram on the right. Imagine Autonomous System 64499 has a few servers under attack. Once the attack is detected, blackholing lets us drop that malicious traffic before it reaches the target. To minimize the impact, we want to drop it as close to the source as possible, ideally, before it even enters our network. In some cases, instead of dropping the traffic outright, we might redirect it to a sinkhole, a system designed to inspect and analyze malicious traffic. There are 2 common ways an upstream provider can trigger blackholing. One is by setting a predefined next hop, which means forwarding traffic to a specific IP address where it will be dropped. The other is by attaching a predefined BGP community that tells the provider's routers to block the traffic. Returning to our example, AS64499 can announce the prefix under attack, tagging it with a special blackholing community, for instance 64499:666. The upstream provider recognizes this community tag and drops all traffic destined for that prefix at its edge routers, preventing it from reaching AS64-499 or congesting the provider's network. Remote triggered blackholing is a widely adopted and effective technique for defending against DDoS attacks by stopping harmful traffic at the edge of the network, before it causes damage. Let's return to the CLI of R1 and inspect the prefixes advertised from R3. We can see that R3 is sending a prefix with the community 65535:666. This is a known blackholing community. Using this tag, we can identify the prefix under attack by running the show BGP ribbon command and filtering on the community value. In this case, the prefix is 172.16.30.0/24. To respond, we'll update our existing policy, import_ISP3, by adding a new ordinal. In the match block, we match all prefixes that have the blackholing community 65535:666 attached. As a best practice, BGP updates that include blackholing communities should not be propagated outside the local AS. So, in the action block, we take 3 steps. First, we add the noexport community to the prefix to prevent it from being advertised beyond our AS. Second, we set the IPv4 next hop to a dummy value, 10.255.255.255. And third, we accept the prefix, since no further processing is needed. Next, we define what should happen with this dummy next hop. Our goal is to drop the malicious traffic, so we create a next hop profile called blackhole, and set its exit interface to null 0. Then, we configure a static route to our dummy address, and attach the blackhole next hop profile to it. Once the configuration is activated, we can verify the result. Running the show BGP fib command, we see that the prefix 172.16.30.0/24 now has 2 communities attached, and the next hop has been rewritten. Finally, the show route command confirms that the outgoing interface for this prefix is null 0, which means the traffic is silently dropped, as intended. Let's summarize the configuration for community-based remote triggered blackholing. First, you need to define a static route pointing to the null interface, which serves as the next hop to redirect traffic destined for the systems under attack. Second, you create a routing policy that matches the blackholing community and rewrites the BGP next hop to the blackholing next hop. As a best practice, BGP updates with blackholing communities should not be forwarded outside the local AS. Therefore, the noexport community is also added to the prefix. Let's add another security concept to our toolbox. In this section, we'll briefly introduce the generalized TTL security mechanism. When you configure an external BGP session with a neighboring autonomous system, BGP messages are typically sent with a time-to-live value of 1. This is based on the assumption that eBGP peers are directly connected. If the eBGP peers are not directly connected, then eBGP multihop must be configured, which increases the TTL value to allow messages to traverse multiple hops. This default behavior, however, creates a potential attack vector. In the diagram on the top right, we see an attacker located 15 hops away from the router under attack. If the attacker sends forged BGP messages with a TTL of 15, they will arrive at the target router with a TTL of 1. Because the router considers the packet to be valid, it must process it, potentially leading to CPU overload and a denial of service condition. Generalized TTL security mechanism helps prevent this type of attack by leveraging the expected TTL behavior between eBGP peers. Here's how it works. If a BGP router sends its messages with a TTL value of 255, and the receiving router is configured to only accept BGP messages with TTL value of 255, then it becomes nearly impossible for an attacker to spoof those messages from a distance. Why? because TTL values decrease by 1 for every hop. So unless the attacker is directly connected, the message won't arrive with TTL value of 255 and the router will simply drop it. This concept is defined in RFC 5082, and it must be enabled on both ends of the eBGP session. While generalized TTL security mechanism can also be applied to eBGP multi-hop sessions, it's less effective in those scenarios, since TTL values higher than 1 are required for legitimate traffic. Now, let's look at how to configure generalized TTL security mechanism in RBFS. The good news is, it's simple. You don't need to manually set the TTL using the eBGP multi-hop command or write custom access lists to filter packets with incorrect TTLs. Instead, you just enable TTL security at the peer group level and define the TTL limit, usually set to 255 for directly connected peers. After activating the configuration, we reset the BGP session to router R3 to apply the TTL security settings. Using the show BGP peer command, we can confirm that TTL security is enabled, and that the eBGP session to R3 won't be established. Running the capture interface hostif 0/0/2 command, we observe that R3 is still sending packets with a TTL value of 1, indicating it hasn't been configured for TTL security yet. To fix this, we switch to the CLI of R3 and enable TTL security. Once configured, the eBGP session is successfully re-established. As we've just seen, configuring TTL security is straightforward. For your reference, I've included both commands on this slide. In the community section, we introduced the concept of remote triggered blackholing, which is used to drop malicious traffic before it reaches its target. While effective, this technique has a major drawback: the target system becomes unreachable even to legitimate traffic. In the following section, we will introduce another method that allows more specific actions. Instead of blocking an entire prefix or IP address, thereby dropping traffic to all ports, it is more effective to implement access control lists at the edge of the network. These allow for more granular actions, such as blocking specific port numbers or applying rate limiting rather than outright dropping traffic. However, this approach requires deploying access control lists across many routers simultaneously, and removing them manually after the attack ends, a process that is both time-consuming and error-prone. RFC 8955 addresses this challenge by defining flow-specific rules that can be configured at a central point upon detecting an attack, and then distributed via BGP to all routers in the network. This central point is typically co-located with the DDoS detection system. The flow-specific rules are then enforced locally by the BGP routers. To distribute traffic filters, multi-protocol extensions to BGP are used and 2 new subsequent address family identifiers are introduced. 133 for flow-specific rules and 134 for VPN flow-specific rules. Flow rules are encoded in MP-reach NLRIs using a combination of components, such as source and destination prefixes, port numbers, and other criteria, along with numerical operators. The corresponding actions, for instance, drop or rate limit, are encoded in extended community attributes. Once the attack has stopped, the flow rules can easily be withdrawn using MP-unreach NLRIs. Configuring BGP Flowspec in RBFS is straightforward. In our environment, the server injecting flow-specific routes is directly connected to interface hostif 0/0/0 and has a loopback address of 192.168.0.100. We first create a new peer group named Flow Server for this server. The BGP session is an internal BGP session, and we enable the Flowspec address family at both the BGP peer group level and the global BGP protocol level. Flow-specific rules are supported for both IPv4 and IPv6, but in this example, we only configure them for IPv4. Next, we add a BGP peer for the Flow server and apply the newly created peer group. Since the Flow server does not run an IGP, we also add a static route to its loopback address. After activating the configuration, the show BGP peer command confirms that a new iBGP session has been established. The detailed output lists the negotiated address families, and we can see that the Flow server also advertises IPv6 Flowspec. We can monitor the receipt of Flowspec rules using the show BGP ribbon command, as with any other address family. These rules result in dynamically created ACLs, which can be viewed using the show ACL command. To wrap up this section, I've summarized the configuration commands for your reference. Configuring BGP flow-specific rules requires activating the appropriate address families at both the BGP protocol level and the peer group level. BGP flow-specific routes can be monitored using the show BGP ribbon command. The output lists the match rules, corresponding actions, and the Flowspec hash. The resulting access control list can be inspected with the show ACL command. The name of the ACL begins with BGP-Flowspec-hash ID. With the growing size and complexity of the Internet, one important challenge is how to prevent issues caused by valid BGP messages that carry incorrect or malicious information. In this context, we explore the resource public key infrastructure, a framework designed to improve routing security in BGP. By default, BGP assumes that all route advertisements received from a peer are legitimate. However, this assumption makes BGP vulnerable to both intentional abuse and accidental misconfigurations. Consider a network scenario where AS64501 receives two route advertisements for the prefix 10.0.0.0/18, one from AS64599 and one from AS64505. In reality, only AS64599 has been allocated that prefix. Public IPv4 and IPv6 address space is assigned by regional Internet registries such as RIPE-NCC, RN, or APNIC, and typically, only one autonomous system is authorized to originate a given prefix. If AS64505 advertises this prefix, it is considered BGP prefix hijacking, which means a malicious AS advertises a prefix it doesn't own, potentially intercepting or blackholing traffic. It can also result from operational misconfiguration leading to unintended route leaks. In any case, these issues need to be prevented. Resource Public Key Infrastructure is a cryptographic system designed to address these vulnerabilities by verifying route origin authorization. It links IP address blocks and autonomous system numbers to cryptographic keys via digital certificates. The central object in RPKI is the route origin authorization, short ROA, a digitally signed statement that specifies which AS is authorized to originate a particular IP prefix, and a maximum prefix length, which sets the most specific subnet that can be advertised for that route. For example, a ROA for 10.0.0.0/16 with a maximum length of /18 would authorize the advertisement of any subprefix between /16 and /18 by the specified AS. Since regional Internet registries manage the distribution of IP address space and ASNs, they also manage the RPKI system. Their responsibilities include issuing digital certificates that bind IP prefixes and as numbers to public keys, hosting RPKI repositories containing ROAs and certificates, providing tools for ISPs to create, modify, or revoke ROAs, acting as trust anchors, forming the root of the RPKI validation chain, While RPKI improves origin validation, it does not secure the entire BGP path, only the originating autonomous system. RPKI is effective only when widely adopted and networks publish their ROAs. In practice, here's how RPKI works. Network operators run an RPKI validator that downloads ROAs and certificates from regional Internet registrars repositories and builds a local, validated ROA database. BGP routers use the RPKI to router protocol, typically over TCP port 323, to query the validator and retrieve ROA data. When a router receives a BGP route advertisement, it checks the ROA database for a matching entry. There are three possible validation outcomes. When a ROA exists, and the prefix and origin AS match, the advertisement is valid. If a ROA exists, but the prefix or origin AS does not match, for instance, wrong AS number or overly specific prefix, the advertisement is considered invalid. Finally, if no ROA exists that covers the prefix, it is declared as not found. Depending on configuration, a router can reject invalid routes outright or apply routing policies to handle them differently. Let's switch back to router R1. RBFS allows BGP prefixes in one routing instance to use the validation database from another. It also enables sharing the validation database between routing instances within the same system. To begin, we create a new routing instance that will host the validation database. Then, we configure a validation session to the cache. In our network, the cache has the IP address 172.16.100.18 and is directly connected to hostIF 0/0/4. We configure this interface and assign it to the validation instance. We also add a loopback interface to the instance. Next, we configure the validation instance using the setInstanceDefaultProtocol BGP command. Then, we define how validated prefixes should be handled using the setInstanceDefaultProtocol BGP peergroup validation filter command. There are multiple options for handling validation results. For example, strict will reject all invalid advertisements. In this example, we choose mark only, which allows us to use routing policies to determine how to handle the prefixes. After committing the configuration, we use the show validation session command to verify the cache connection. The output indicates the session is established and shows that 10 ROAs have been received. Running the show validation database command lists these ROAs. Finally, the show BGP ribbon command displays flags in the first column, reflecting the validation state of the received prefixes. To wrap things up, here's a quick summary of the steps involved in configuring RPKI in RBFS. We need to define a validation session to the cache. This can be done over IPv4 or IPv6, and you can optionally specify a custom TCP port. Optionally, we can create a separate routing instance to host the validation cache. This isn't strictly necessary but can help organize your configuration. Afterwards, we need to enable RPKI by setting a validation instance in the BGP settings, and define how the router should handle validation states at the peer group level. You can monitor validation sessions using the show validation session command. The ROA database downloaded from the cache can be viewed with show validation database. And finally, you can verify the validation state of received prefixes using the show BGP ribbon command. This brings us to the end of BGP Part 2. As you've seen, BGP is a complex protocol with a wide range of configuration options, and we've only touched some of them. Across these two videos, we've focused on the most essential features to get you started. I hope you found this clip helpful and enjoyable. Thanks for watching, and see you in the next video.